Imagine a world where light is manipulated with the precision of a surgeon's scalpel, revolutionizing communication and information technology. This is not just a dream, it's a reality being shaped by exciting developments in the field of photonics. Researchers have recently unveiled an innovative technique that utilizes spin-orbit coupling in van der Waals, VDW materials, to generate optical vortices with remarkable control and efficiency. This breakthrough lies at the merging point of two cutting-edge domains: the burgeoning field of two-dimensional materials held together by van der Waals forces, and the complex art of manipulating the angular momentum of light. By tapping into the unique spin-orbit interactions present in these atomically thin crystals, scientists are opening up new avenues for creating optical vortices, structured beams of light that possess orbital angular momentum, OAM, which hold promising implications for the future of optical communication, advanced microscopy, and quantum information processing. Optical vortices set themselves apart from ordinary light beams due to their distinct helical wavefronts and central phase singularities, giving them a unique corkscrew shape. These twisted beams carry orbital angular momentum, allowing them to encode information in the patterns of their twists, as opposed to the more commonly known spin angular momentum connected to the polarization of light. The scientific and technological communities have been captivated by the potential of optical vortices, notably their ability to multiplex data channels, achieve enhanced resolutions that surpass classical limitations, and manipulate microscopic particles. Traditionally, generating such vortices has required bulky apparatus like spatial light modulators or spiral phase plates, which restricts their integration and dynamic control within compact photonic devices. This is where van der Waals materials come into play. Innovative layered crystals that include materials such as graphene and transition metal dichalcogenides, TMDs. These materials are celebrated for their remarkable electronic, optical, and mechanical properties. The unique structural anisotropy and reduced dimensionality of these materials lead to significant spin-orbit coupling effects. This means that the intrinsic spin of electrons is closely linked to their momentum. By capitalizing on these inherent microscopic interactions, the research team has demonstrated that VDW materials can function as ultra-thin optical elements, capable of converting spin angular momentum into orbital angular momentum directly, thereby acting as novel optical vortex generators. The crux of this groundbreaking research hinges on the manipulation of spin-orbit coupling within these two-dimensional materials to simultaneously shape the polarization and phase of light. This intricate relationship is vital, as spin-orbit coupling enables a connection between light's intrinsic spin, polarization, and its extrinsic orbital motion, which is responsible for vortex formation. Through the careful design of VDW heterostructures and optimizing their interaction with incoming light by adjusting crystal orientation and stacking, the researchers successfully exploited spin-dependent phase shifts that influence the helical wavefront of the resulting optical field. To achieve this, they utilized advanced fabrication techniques that allowed for layers of VW materials to be stacked with extraordinary precision down to angstrom levels. This meticulous control enabled tunable strengths of spin-orbit interactions, leading to the generation of high-purity optical vortices with customizable topological charges, parameters that determine the number of twists or windings in the phase front surrounding the beam's axis. These topological charges are crucial, as they define the vortex beam's capacity to carry information and its possible interaction modes. The capability to create a variety of vortex states using singular ultra-thin components heralds a new era where compact, scalable photonic devices can enhance communication architecture. One of the most intriguing aspects of this research is the dynamic adaptability and integration potential of these VW-based vortex generators. Unlike traditional static diffractive optics, these materials can react to external stimuli, such as electric fields or mechanical strain. This provides an actively reconfigurable means to control the generated optical vortices. The ability to modify vortex beams in real time is essential for adaptive quantum networks and programmable photonic circuits. Furthermore, due to their ultra-thin profile, VDW materials facilitate seamless on-chip integration with existing silicon photonics platforms, thereby creating an important linkage between quantum photonics and mainstream photonic technologies. The implications of this finding reach far beyond just optical communication technologies. The precise control of spin-orbit coupling in VDW materials opens new experimental avenues to investigate light-matter interactions at the nano and quantum scales. For example, customizable optical vortices could offer unique interactions with chiral molecules, paving the way for sensitive detection methods for various biomolecules or their enantiomers. Moreover, this phenomenon could enhance optical tweezers and the manipulation of nanoparticles, as the light's angular momentum can exert both torque and forces at microscopic levels. By leveraging the spin-orbit effects inherent in VDW materials, we can imagine generating optical traps with significantly improved functionality. From a fundamentals perspective, the ability to convert spin angular momentum into orbital angular momentum within these adaptable materials both challenges and deepens our understanding of quantum electrodynamics in lower dimensions. The intricate balance between spin, valley, and orbital degrees of freedom in two-dimensional crystals provides fertile ground for discovering new quantum phases and topological phenomena. The methods established by this study facilitate the exploration of tailored spin-orbit coupling that aligns with specific optical responses, potentially catalyzing breakthroughs in the fields of spintronics and valleytronics. On a technological front, the innovations presented in this study have the potential to transform the design principles of integrated photonics. This could lead to smaller, multifunctional devices adept at managing structured light. Data centers and telecommunication infrastructures could see dramatic advancements as VDW materials enable multiplexing schemes based on both polarization and phase characteristics. Such systems could significantly boost data throughput while also minimizing energy usage and physical space requirements. Additionally, the precision achieved through the VDW spin-orbit coupling mechanisms is poised to enhance the protocols of optical quantum computing, where complex photon states are used to encode information. The study also emphasizes the obstacles the researchers had to navigate to control fabrication imperfections and external environmental factors, which could potentially compromise both the quality of the optical vortex and the spin-orbit effects. The team employed rigorous characterization techniques, such as near-field microscopy and polarization-resolved measurements, to validate vortex generation and the assignment of topological charges effectively. This thorough approach not only ensures reproducibility, but also provides a roadmap for translating laboratory successes into commercially viable technologies. Looking to the future, the authors of this study envision a scenario where these VDW optical vortex generators could be integrated within multifunctional photonic circuits that include components for detection, modulation, and nonlinear processing. This integration has the potential to create holistic systems capable of producing, controlling, and routing structured light signals all on a single chip. The researchers also suggest exploring new heterostructures made from diverse VDW crystals to refine the spin-orbit interactions beyond current capabilities. Furthermore, adapting this technology for applications in mid-infrared or terahertz frequencies represents another exciting direction, which could significantly impact imaging and sensing technologies in those spectral ranges. Importantly, this work inhabits the larger context of achieving nanoscale control over light-matter interactions, a domain that has ingeniously transformed both nanophotonics and quantum optical technologies during the previous decade. Moving beyond mere passive interactions, the active utilization of spin-orbit coupling in VDW materials marks a pivotal change in the design of functional optical elements. The scientific community is equipped with newfound levers to precisely engineer the spatial, spectral, and polarization properties of light at an atomic scale, successfully overcoming fundamental challenges inherent in classical photonics. In conclusion, the intersection of spin-orbit coupling effects and van der Waals materials to generate optical vortices signals a remarkable advancement in both photonic science and technology. The sophistication, control, and tunability achieved through this research is set to enhance applications across telecommunications, quantum computing, biosensing, and more. As the realization of these concepts progresses, the combination of two-dimensional quantum materials with advanced light manipulation techniques may usher in an era where bespoke light-matter interactions serve as essential building blocks for the technologies of the future.